Hello guys, welcome to Recitation 3. This is a momentum and impulse problem. So, just to introduce, we know that from Newton's second law, net force is mass times acceleration. And we know acceleration is V final minus V initial over time. So net force times time is change in momentum, mv final minus mv initial. So change in momentum is the same as what we call impulse. So this impulse, this change in momentum. So when your forces interact for a given time, it's equivalent to your change in momentum. So that's what's going to happen here. So two kids play on the ice where friction is small enough to ignore. The boy has a mass of 30 kilograms. So I have mass of boy, 30 kilograms. And the girl has a mass of girl, 40 kilograms. They push off each other's hands for 1.5 seconds. So t is 1.5 seconds. So that they move apart. During the time they are pushing each other, they both accelerate backwards immediately. Immediately after they push each other, the boy's velocity is plus 6 meters per second. So the boy's direction is plus, the girl's direction is minus. So we have to take note of this. The boy's velocity, so v boy is plus 6 meters per second. Is that okay? So use the sign convention. Show what is the acceleration of the boy. So let's see. So they start from rest and then they push each other. Okay? Okay? So let's look at the acceleration of the boy. So I know for the impulse for the boy, then the net force on the boy times time, 1.5 seconds, is the mass of the boy times the velocity of the boy. So the mass of the boy is 30 times velocity times 6. So from here I can get the net force on the boy. So the net force on the boy is 30 times 6 divided by 1.5. So let's see what that gives us. That's the net force on the boy. 30 times 6 divided by 1.5. 120 newtons. Note, that is the force on the boy. That is going to be the same magnitude of force on the girl, but with a minus sign when we get there. So this net force on the boy is the same as the boy's mass times acceleration. So the acceleration of the boy is the net force divided by the mass of the boy. 120 divided by 30. 4 meters per second squared. Good. Now the next problem is, what is the force that the girl exerts on the boy? So this is for the A part. For the B part is minus 120 newtons, because we already got that, minus 120 newtons. What is the force that the boy exerts on the girl? We already got that. C part is 120 newtons, plus 120 newtons. Okay? So, the force that the girl exerts on the boy, the B part, the force that the girl exerts on the boy is the one that is positive, is going to the boy. The one that the boy exerts on the girl is the one that's negative. Okay? Very important. Because it's pushing the girl to the other side. What is the force that the boy exerts on the girl? That is C, negative. What is the magnitude of the acceleration of the girl? So we use this force that the boy exerts on the girl equals, so for the D part, minus 120 equals mass times acceleration of the girl. So acceleration of the girl is minus 120 over mass of the girl, 40, minus 3 meters per second squared. Is that okay? But they're asking for the magnitude, so we forget the minus. So just say 3 meters per second squared. So this is confusing. Magnitude only, forget the minus. Just 3 meters per second squared. Okay? Then E, what is the velocity of the girl immediately after? So the velocity of the girl immediately after. So we're going to use the moment equation. So net force times time equals mass times velocity. So net force for the girl is minus 120 times time, 1.5, equals mass of the girl, 40 times velocity of girl. So velocity of girl is minus 120 times 1.5 over 40. Okay? Is that okay? That gives me 3 times 1.5. Is that okay? Minus 4.5. So E is minus 4.5 meters per second, because the girl is going in the negative direction. Okay? So that is it. A part is 4 meters per second squared, B 120, C minus 120. D, because they're asking for magnitude, is just 3 meters per second squared. And E is minus 4.5 meters per second for the velocity of the curve. Okay? Okay. Thank you guys. Have a good one.